Alright, continuing in this series of videos, analyzing the notions of conventional physics regarding function of the elemental portions of the universe. Something like that. The little stuff. What's it doing and why is it doing it?
Here I have 1 square meter. And radiation is coming in. And I know exactly how much radiation is coming in. For every square meter, there is this value S. So S, which is an energy per square meter per second. Remember, that's the dimension.
The Poynting vector. Poynting vector.
Of the Poynting vector. If I divide this by C, and I divide this by C, then look what I have here. I have energy divided by C. But the energy in electromagnetic radiation divided by C, according to Einstein, is momentum. And I don't care whether this is 100 billions of individual photons. That's okay with me. That is a momentum. And so I have now a momentum per unit time that makes it a force. But a force per square meter makes it a pressure. And so this is pressure.
Yes, that's exactly what a force is pressure. That's exactly right. So I don't know why that's a surprise. What else does a force do but apply pressure? Yes, exactly.
And we call that radiation pressure. It means that if you are...
It's the same pressure for sound, for any kind of pressure. There's no other kind of pressure but pressure. The answer is what energy is always in the form of is some form of pressure. Stuff moving. Yes, pressure.
Exposed to bombardment of electromagnetic radiation, and you absorb it, that you feel a pressure. The radiation comes to you, and you're being pushed backwards. And this is the pressure that you will experience.
Not necessarily being pushed, because what the pressure can be doing is blasting pieces off of you. It can be knocking little bits off of you. It can be heating you. It can be doing other things. The energy of the pressure can be felt in all kinds of directions besides that way. So it can hit me this way, but it can cause me to move that way, at least pieces of me.
It makes a difference whether the radiation is absorbed or whether you are capable of reflecting that radiation, just like...
So it's always absorbed, and the only question is for how long. So it's always taken in, and then in some way U-turns. So you could argue that it's all U-turns. Nothing ever purely bounces off of something. It always U-turns is kind of the way to look at it. And the question is how deep is the U-turn? How many miles down the highway do you go before you reach U-turn?
With the tomatoes. And so if I'm trying to be as general as I can, let me first of all specify the mean value of S. That's the only thing in electromagnetic radiation was measured. It's the mean value.
Yeah, okay, so some average pressure or average energy over a period of time kind of a thing. So again, just thinking of something called the Poynting vector as energy, it's not very good semantics, but that's what it is. It's an amount of pressure.
So the mean value then, if I divide that by C, and I multiply that by a vector alpha, you will come up shortly and tell you what alpha is, that is now the radiation.
So that's probably some silly relativity nonsense or something.
Pressure. And alpha, if alpha is 1, then I have full absorption. All the radiation is absorbed. If there's no absorption, if it's completely transparent and there is some radiation that goes straight through you, then alpha is 0. But if there is 100% reflection, which can happen, you can reflect radio waves from metals with almost 100% reflection, then alpha is 2. So then you get twice the pressure.
Right, but that's not really true, because that's basically, that's like a tennis ball hitting a tennis racket. You know, two springs. just, you know, so I don't know how to say this exactly. But yeah, it's not really double the pressure. Your reaction is separate from the action. The pressure itself doesn't change. The amount of pressure that hits is exactly the same. The only thing that's going to change is how you react to it. And you can react to it, you can overreact. You can be capable of taking it in, using it, and then throwing it back, which is two actions.
If you take the sun, whereby the mean value for S is 1000, you can calculate now, if you absorb that radiation over 1 square meter, what the pressure would be that you would experience. So your body, 1 square meter, you expose it to the sun in the direction of the sun. That force is insignificantly small. The pressure would only be 3 times 10 to the minus 6 newtons per square meter, because you have to divide that number thousands by...
So we're dividing watts by newtons now, you know, which is, or something like a newton, a C. So we divide it by the speed of light, and that somehow gets us a newton.
See, there's not much left over. And if you hold your hand up in the direction of the sun, your hand would only have an area maybe of 1/100th of a square meter. That force is unnoticeable. So in our daily lives, we don't experience radiation pressure very much. Regardless of whether you think of electromagnetic radiation as plane waves, or you want to think of them as spherical waves, or you want to think of them as photons, I really don't care. But what...
See, I know, you know, I really don't care, but this is so fundamental to physics, this understanding this elemental function, and it's fundamental to the math being comprehensible even, is some understanding of exactly what the mechanisms are. So this is a place in physics where they should say, yes, we have a very incomplete theory because I can't tell you whether it's a round wave or it's a flat wave or whether it's actually a corpuscle. And yet they'll say it. You know, they'll say nail in the coffin, evidence that it's a wave. They'll assert that it's a wave whenever possible, and yet they'll have this little, every now and then, they'll make this cautionary statement that yes, it is reasonable not to accept our declarations because they're based on almost no facts.
What matters, as far as radiation pressure is concerned, is how much power flows through 1 square meter and which fraction of...
That was a pretty girl. Yeah, that was a pretty girl.
That energy is absorbed, or maybe some of it even reflected. So the radiation pressure is not that important in our daily lives, but it is important in astronomy. And in fact, you can see it. Some of you can see it. A comet has 2 tails. And one of those tails is the result of radiation pressure. A comet is made of carbon dioxide, and it has also dust. It's about the size of Manhattan. And when it gets close to the sun, the radiation pressure of the sun, which is this radiation pressure that we just talked about, pushes onto the dust particles, forming the tail, and this tail is white light, white yellowish light, which is reflected sunlight of these dust particles. And then there is a second tail, which is bluish, which is hard to see with your naked eye.
Smaller particles.
And that one is the result of the solar wind. We discussed the solar wind earlier. Causes the aurora in the upper atmosphere of the Earth. The solar wind are protons and electrons, which are emitted by the sun in a rather erratic way, sometimes a lot, sometimes not so much.
So I'm calling them solar wind, it's because they're more like a plasma. So they're only moving because they are together, electrons and protons. So they're almost in the form of some other kind of nuclear bits, not really in the form of independent particles.
And they move with a speed of 250 miles per second or so, and they ionize the CO2. So they excite the molecules. When you have de-excitation of the molecules, they emit blue light.
The de-excitation, so he edited himself here and you couldn't really tell what he said, but he was talking about the de-excitation of the molecules, which means the deceleration of the electrons and protons, which emits the light, actually, as I would argue. that's where they come. That's where the photons come from, is between or inside of electrons.
So you get two tails, and we'll show you these two tails. The tails can be 100 million kilometers in size. They can be huge. As some of you may remember, or should remember, in 1997 we had a fabulous example of a comet which was Hale-Bopp. I watched it every night for months on end. This is a picture that you're going to see of Hale-Bopp, which is a time exposure. It's not what you can see with your naked eye. In fact, frankly speaking, I have never seen the blue tail, but the white tail, which is the one due to radiation pressure, I have seen many, many times.
Yes, I find them totally unfascinating. All that, you know, meteor shower stuff and the rest of it. Just couldn't possibly care less.
So let's take a look at Hale-Bopp. And there you see it. And you see clearly the two tails. You see the blue tail here, which is the result of the interaction with the solar wind. And then here you see the dust, which is the result, the tail is the result of radiation pressure. The sunlight is absorbed, fully absorbed by these dust particles.
Yeah, so that's their theory anyway, so they're stating it. I would argue that you do get blue light with small particles, so it could be that that's just small particles, but whatever, doesn't really matter.
And it's pushed away. I just wonder who has seen Hale-Bopp 3 years ago? Yeah? Just hold your hands up, I'm just curious. It was a spectacular sight, and it was easy to see for months on end, you could see it. You don't see very bright comets all that often.
I mean, it did the smoke thing, you know, where the big smoke, the big blobs appear white, the little particles appear blue. You know, so size is important in this case.
So without being very quantitative in terms of the electric and the magnetic field strengths, it is easy to determine the direction of the oscillating electric field if we know in what direction the charges were being oscillated. And that has to do with the polarization of the radiation, and so I would like to spend the remaining time today on that. And let's stick to the center board.
Alright, so this should be interesting because they don't really understand what polarization is, so they've just metaphored it into their model of their two-wave thing, and but it's just a construct, you know, for mathematical purposes. It's an abstraction. I don't think it has anything to do with the truth.
So we have a oscillating charge being accelerated, and I will choose a coordinate system like so, and let's suppose we oscillate the charge in this direction. Acceleration all the time, and the frequency is omega. And we are somewhere in space here, and we receive electromagnetic radiation. We are at point P. I'd like to make you see it three-dimensionally. And at this angle, b theta, and this is the position vector r from the origin of the oscillating charge to where you are. You are at point P. And when you are at P, I'm going to give you some very simple rules which will always allow you to determine the direction of the electric field. The electric field...
Alright, so again, there's only one thing happening. There's radiation coming off of the object, and as you're moving it, you know, like little rays, obviously as you're moving it, those lines, or those rays, are being animated from different points. And so, instead of being nice straight line rays, they're being broken rays. You can sort of, you know, if I'm shooting bullets and I'm going up and down while I'm shooting the bullets, right? So if I stay still, I'm just shooting the bullets. They're a nice long ray of bullets. But if I'm moving, the bullets are also moving to different positions. So they're in different locations in their path. The first one I shoot will end up here, and then the second one I shoot will end up here, and the third one here, and the fourth one here. So they're now becoming rays in a different form from the position I was at, essentially. It's a little complicated, but it's all really about speed. And well, I don't want to say it's all about speed, but we're continuing.
Is always perpendicular to the direction position vector, the direction of propagation. So you're looking in this direction to the charge. The electric field that you experience, if the charge is doing this, is always perpendicular to R.
A little hard to see that from this drawing. I mean, perpendicular should be this way, but we'll just play along.
And A and R and E are always in one plane. And notice, that's the way I drew it in the blackboard. E and A and R are in one plane.
Right, so the three dimensions, always two of the three dimensions are in one plane. Okay, left, right, forward, back, and up and down are in the wrong plane. So that's what he means by that.
So it's extremely simple. So if this is oscillating with angular frequency omega, then this electric field will also be oscillating with an angular frequency omega. If you double the charge, the electric field will double.
So again, the field has been created by the object. So of course, anything the object is doing, the field will represent that doing. You can't move it without noticing. Just like the photons coming off of the thing you're moving are coming off of it from different places as you're moving it. I'm not going to see the same surface anymore. As I move this object, I'll see reflections off different locations. Because it's moving, obviously, and I'll see it here instead of here because it's moving.
If you double the acceleration, the electric field will also double. That's reasonably intuitive. So the electric field strength is proportional with the charge that you oscillate with the acceleration. And then there comes this effect that we discussed there, that nothing goes out in the direction of the acceleration. No energy goes out in this direction, so no electric field is produced in this direction, and the maximum is produced in this direction, and somewhere in between here, and that is then reflected by the sine of theta. If theta is 0, nothing goes out. If theta is 90 degrees, you get a maximum. That's the whole plane perpendicular to this oscillating charge, this whole plane, maximum electric field. And
the charge can't be oscillating in free space without something causing it to oscillate, quite obviously. So the idea that there's nothing coming out the other end is sort of a non sequitur, because obviously the only way it can stop and then move again is that a force has to be applied to it in that direction. Nothing can oscillate on its own, just say for fun. There has to be a mechanism. There has to be objects it banging into, or there has to be forces acting on it. There has to be a mechanism that's causing the oscillation. And there's no known mechanism, I don't think, like Mexican jumping bean or something, that the force can come from, an oscillation like that can come from inside the object. So it always has to be because there's a force being applied from the external world. So the idea that you could measure a force coming out the end wouldn't make much sense, because in the context of the circumstance, that can't happen.
then, and that may not be so obvious to you now, it's also inversely proportional to the distance r. If you double r, the electric field strength goes down by a factor.
So that's a charge. So a monopole is the R rule. A magnet, a dipole, is the R squared rule. And the R cubed one is on the plane of the magnet that would be dead middle of the two forces. If you go on the same plane as the north pole of the magnet's up here, the south pole is here, if you're on that plane, then you're R cubed.
Of 2. And the Poynting vector, which is the product of...
Well, technically, he says if the magnet is north-south, it's R cubed, which I don't think is true.
E and B, but E is always proportional to B. So the Poynting vector then is proportional to Q squared, proportional to A squared, proportional to the sine square of theta, and inversely proportional with R squared. And that is obvious that it has to be
So whether any of that is obvious, you just squared everything. So I don't know why we wouldn't just cross out all the squares and just forget about it. So that doesn't make a hell of a lot of sense to me.
Inversely proportional with r squared. Because if you have a sphere, and radiation goes out, and you're twice as far away, then you know that the area of the sphere is 4 times larger. And so the amount of power per square meter must be 4 times lower.
So then why are we doing this then? Why did we pretend that a point charge is acting somehow differently? See, that's where it just doesn't make much sense. Yeah, sorry, didn't follow that.
But the Poynting vector must fall off as 1 over r squared. That's a conservation of energy. And if you accept the fact that the Poynting vector falls off as 1 over r squared, then the E vector must fall off as 1 over r. Because the Poynting vector is the product of E and B.
So this is the cheat. Okay, there. So we're back to the fact that they've turned a single force, which the Poynting vector is recognizing, the whole force, and they're back to splitting the E and B part, which then you would have r squared if you count both fields. It's only one field, there's only one force, and so it's an r squared rule. Alright, so charges, a charged monopole charge is the r squared rule, not what I said before, the r thing. So they're just making these things more confusing than necessary.
E and B must both fall off as 1 over r. I want to show you.
They're just taking, like, in its 3 dimensions, you have this. Say if I'm shooting a ray out, right? I'm moving something in this dimension towards you. And the only relevant dimensions are up, down, left, and right. So what they're doing is just taking this dimension and this dimension, calling one of them magnetism and calling one of them electricity. When if it was gravity, they'd have recognized the gravity is both going both ways. It's one force. It goes this way. It spreads at a distance. It spreads this way and it spreads this way, meaning it's a square rule, meaning it's 4 times weaker with twice the distance. The r squared rule. And so they're just sitting there playing this game like we'll just talk about this way first and then we'll talk about this way second. And there's no reason to do that.
A picture that may help to see you how the radiation, how the electric field is oriented relative to a charge that we are accelerating. In the middle here, we accelerate.
So this is just absolute rubbish. There's nothing's doing this, nothing's doing that. It's just nonsense.
Accelerated charge up and down. Frequency omega. Whatever radiation you want to make, fine with me. You can make omega as large as you want to.
So now they're imagining this charge as something like an electron or something, and it's changing its positions and somehow shooting something from these different positions or something. None of that's happening. There's no ropes, there's no strings, there's no any of this extra distance is traveled. None of that happens. It's a compression or it's a corpuscle. Think of it that way. It's space compressed, if you want to think of it ether, or it's a little bullet. But that's all there is. There's a compression or a bullet. There's no this.
For one thing, notice these waves here, these snakes, represent electromagnetic radiation.
Represent, but are not representative of. They're letting them represent it based on an amplitude, or a volume that you'll judge by how big this snake is. But the snake doesn't have anything to do with the reality, beyond being a way of representing it. But it's not representing its realness. It's just representing a property it has.
Nothing is going out in this direction, and we understand why.
I mean, you could represent me by a wave that's 6'1", and say, there, that represents my impact on Earth. It's not me.
The maximum is going out in a plane perpendicular to this direction. That is this, and this. And notice that the E vector that you receive when you were here is perpendicular to R. This is R, and it is perpendicular. And notice what I said, that A and R and E are in one plane. A, which is the acceleration, R and E are in one plane. A, R, and E are in one plane. A,
Yeah, sorry, I can't see his laser pointer, can't see anything, so I don't know what he's talking about again, but whatever, doesn't really matter.
R and E are in one plane. So you can always determine the direction of the oscillating electric field. And if you go at an angle theta, which is neither 0, which it is here, nor 90 degrees, which it is here, here, and here, but if you have something in between, then notice that the E vector here is drawn a little smaller. So that is that sine theta here. And consequently, the Poynting vector in that direction will be smaller than in this direction. And in this direction, the Poynting vector will be 0. We call this radiation, whether you're here or there or there or there, we call it linearly polarized radiation for the simple reason that the electric field is oscillating in one direction. It's linear.
So again, it's the there's no oscillation, and as I've pointed out, another way of understanding polarization, another way of representing it, another argument for how it is in reality, a different argument of the reality, would be that polarization just has to do with when photons are emitted from electrons, the electrons are in a state moving, and they're in materials that are moving, and they're in all that stuff. So when they release photons, their position changes. So as they're vibrating, which I would argue they are doing, but they're actually moving in towards you and away from you. But anyway, when they're doing that, they release photons when they stop and start. So, well, when they stop for sure. So when they have momentum and they stop, they release a photon, a piece of a photon. When they do that at a regular frequency, it's a photon. It's a ray of light. So when they go like this, they release something. Not my fault. But the idea would be is if the electron is moving while this is happening, then some of the little bits go out this way, here at this angle, at this level, and some might be released at this level, and some might be released here and here. So they might be released at somewhat sloppy. So their alignment as bullets isn't perfect. So they aren't on a perfect line. And if they are, that's circular polarization. But the odds are they're going to be a little bit off based on the frequency. So you can see the timing cycle will give them a certain amount of time to move. So if it's radio waves, there's lots of time in between the photons being released, so they can move quite a lot. If it's photons of visible light, they have less degrees of freedom, in the amount of time between the frequencies. There's not enough time to get too far off. And as you get higher and higher in the frequency, the polarization gets tighter and tighter. And that's another way of representing the reality. I would argue closer to the truth than this wavy, ropey, liney stuff.
And I'm going to produce for you linearly polarized radiation, and I have 2 demonstrations for that. So I'll get the lights back on again. So let's discuss these demonstrations. I have here a transmitter which transmits at 10 gigahertz.
Alright, so this is the radar again, your microwaves, however you want to describe them. And the problem is he puts a sound tone on them, so he's not measuring the actual radiation. He's always measuring how much of the signal he can receive. So, but he's not going to be doing double slit stuff. He's just going to be doing the grading to block the signal.
That is a wavelength of 3 centimeters. You wouldn't call that radio, you would call that radar, but that's just a matter of names. And we have also a receiver. We have a transmitter and we have a receiver. The transmitter is here, and the receiver is here. If I give you a 3-dimensional picture, this is my...
Alright, so the stuff that's sort of not pointed out is that these radar devices are completely dependent on an oscillating capacitor to function. So they're already pre-tuned in a sense, so they can't pick up any signals from other sources because they have to vibrate a certain capacitor at a certain speed, and that's it. And they have sort of the narrow kind of band, and that's it. That's the end of their function as a regular radio receiver, so an emitter. So it does narrow the utility of this as an experiment.
Coordinate system, this is coming straight out of the blackboard to you. That's what I meant by this. Then the transmitter is aimed like so, just like this. Current is going to be oscillating like this. And the receiver...
So again, the current won't be oscillating like that. It will be coming out of the horn this way as photons. And all that's going to change, I mean, all that's really being affected is, what's the right word to say it? The position that they're emitted at. So just like on a long antenna, the photons are emitted at different locations. He's just basically saying the antenna wire inside the horn is this position or it's in this position. But that's essentially all it is. It's just saying which way is the antenna pointed, this way or this way.
Receiver, think of this as my radio, which is receiving, is here. And the antenna of the radio is also in this direction.
So now he said it the right way. The antenna is in this right position. So again, the charge, the electricity is going through the antenna, and to call it oscillating charges isn't really right, because all you're doing is pressurizing, you're creating a voltage and at a frequency. So you're increasing the pressure, decreasing the pressure, increasing pressure, decreasing pressure. You're not necessarily, the movement part isn't the part that's critical to the creation of the magnetism, essentially.
And so the electric field, which you see here, which comes from these oscillating charges, which oscillate, by the way, at a horrendous frequency, 10 billion times per second, that electric field is perpendicular to R. This is R. And the electric...
So it could be called the magnetic field. It just doesn't matter. The field is photons. They're just not in a form that you can see. But they're exactly made of the same bits that a photon's made out of. So if you could up the gigahertz to nanohertz or whatever, you know, the speed of light, the vibration speed of light, then you would have light moving. And then you'd be able to, well, you still wouldn't see it moving across, but you could have it reflect off a surface and say, ah, look, it's light coming out of that antenna. But that's what it would be. It would be light coming out of the antenna. The radiation of a light bulb is the same form as magnetism. It's just at a frequency.
Electric field, R and A are in one plane. Ah, so that means that the electric field that arrives here is oscillating like so. And therefore this antenna, this receiver, is very happy. The radiation comes in exactly in the right way. And
so again, it has nothing to do with oscillating. It has to do with pressurizing it. As he pointed out before, it's radiation. It imposes pressure. It pressurizes. It pushes against the conductor. When you push against the conductor, it creates the pressure in the atoms. The atoms, it's a conductor, so the pressure moves through the conductor. And as you're turning it on and off, on, off, on, off, the pressure is going back and forth, back and forth, back and forth. I mean, but see, he's sort of describing like somehow there's a charge doing that, and there's not a charge doing that.
So it will receive it. We have modulated this signal with an audio signal, amplitude modulation, as we discussed that earlier, that you also use with radios. And we modulated with approximately 1 kilohertz audio signal. And we'll make you listen to that audio signal. You can tell then that this receiver is indeed receiving the 3 centimeter radar from this transmitter. That's what we will first do. So I'll just turn on the transmitter, and here you hear 1 kilohertz.
So again, it would be better if what they were doing was detecting the actual radiation, that is, measuring how much radiation gets to the other receiver, rather than complicating this story, you know, by adding, you know, variation, not just an up and down signal, but changing it to a signal that varies. But again, it doesn't really change anything for this experiment. In other experiments, it does matter.
This is the modulated signal, and it's received by this antenna, which is a straight wire like this, and this is the emitter. And to demonstrate to you that it really goes from here to here, I put my hands in between. My hands absorb 3 centimeters. It's not there anymore. There it is. It's not there anymore. But now...
Alright, so that would be an interesting thing to discuss, is why would it matter? So at 3 centimeters, if he puts his hands together, it blocks it. I don't know if he put a single hand, whether it would matter. Because yes, that is less than 3 centimeters, probably, a little less. So that would be an interesting subject. Why does it? Why is the signal? What's happening to it? Is it scattering? What exactly is breaking the signal? And does the radiation still get through your hand? So if I was actually detecting radiation, see, that would be a case where, yes, the signal's been broken. That is, the frequency isn't the same because it's been scattered. But the actual amount of photons getting to the other side is the same. So it's sort of like me sending light with an image through something, and the image doesn't survive, but the light does. And that's sort of what I would argue is what he just did. What he did was just block the arrangement, because he created a bunch of scatter through his atoms. They scattered the signal, broke the continuity of the rays. Now the rays are wildly polarized, because their vectors were changed. So one bullet was going this, they were all lined up bullets, and now one of the bullets is out. So now you can't detect the frequency because the frequency is wrong, because one bullet went this way or went that way. Still went towards the target, mostly. Part of it obviously reflected off his hand, but clearly some went through, and now it gets to the other dish, but it doesn't get there with any continuity. The frequency's been broken. The image is lost. So it's like shooting light through an opaque piece of plastic or something. The image is lost, but the light will still make it.
Now I'm going to rotate this antenna by 90 degrees. So this one is going to be put in this position. So now the electric field, so I'm going to put it now in this position. So the electric field now is going up and down like so. But the receiver doesn't like that, because the antenna of the receiver is like this. So it cannot drive any current, and so you won't hear anything anymore. So what it means is that I have changed the direction of polarization by 90 degrees, and the receiver...
Well, you've just changed the antenna. So obviously the antenna has radiating consistent with its length. And by changing its length, okay, now the other antenna is just receiving one sliver. So it's just receiving one sliver of what was before. It was receiving all the slivers. So if you just drew circles around the antenna, a bunch of like 10 circles, you could sort of understand that when the circles and circles are lined up, it's going to work, that they'll transfer to circle to circle. But if I turn it this way, well, all of the energy coming off this part of the antenna isn't going to hit any circles.
Cannot see that. I'm going to rotate it now 90 degrees, and it stops. So now the electric field goes like this. The wire here, the antenna is like this, and the wire says, sorry, I can't hear you. But all I have to do now...
So, but that's, like I said, it's really not what the problem is. The problem is the radiation is coming off as rays. So it would just be the same thing as light. If you had a sliver cut in a piece of cardboard, and then I have another piece of cardboard with a sliver in it, and we have them lined up, well, I'm going to see a lot of light. I turn it this way, I'm not going to see shit. I'm going to see one little dot.
Is rotate the receiver 90 degrees, and so I can rotate this antenna and put it vertical, and then of course it's happy again. So if I rotate this 90 degrees, there comes the signal back. So now the E field is like so, and the antenna receives it like so.
Like I said, this is where it gets, in my opinion, this is a little bit underdeveloped, undercooked, because again, the explanation could be as simple as the one I just gave you with slits in cardboard. The radiation is coming off in a certain way, and yeah, you're not going to receive it if you close the door to the way the radiation's coming in.
Now I have one great teaser for you. And I want you to think about that. We can actually have a vote on that. I have here a wooden frame with metal bars. No trick. Metal bars. And I'm going to put that in between here. So we have the situation that we are transmitting electromagnetic waves with the E field going like this, and the receiver is perfectly happy. The receiver is also aligned like this. There you have it. I can put this grid in like so that the bars are in the same direction as E, but I can also put it in like so that the bars are perpendicular to E. If I make you a drawing, if you would look in this direction, then I can do one of two things. Either the bars are like so, or the bars are like so, but in both cases is the electric field coming in like this. Who thinks that if I have...
So the idea is that it's polarized, this radar signal. Besides being the antenna, you could argue is in a sense a polarizer, because it has a length and not a, the width is irrelevant. It doesn't have a, if you made an antenna that was an X, well then it would be polarized in both directions and it wouldn't matter which way the grid was, because you get half the signal either way. And so the real question is how is the signal interfered with by the bars? And the idea is just recognizing, well, which way are the electrons moving, okay, when they're creating their signal. Are they moving this way through the wire, which seems to be the argument? Are they moving this way inside the little piece of wire? Now, it doesn't seem very likely they're doing this inside the wire, so straight up and down wouldn't be the filter. The filter would be cross. So they'll get through the one going this way, horizontal, because they're moving horizontally. I think that's where he left off with the antenna. See, now I'm not remembering which way the antenna is. The antenna is, can I tell by just looking at it? They look like it's going, the antenna looks like it's going this way, horizontal. So that would mean the electricity, the polarization is horizontal. That means it'll get through the horizontal bars and get blocked by the vertical bars.
If the bar is vertical, that the electromagnetic radiation will go straight through without any problem. Who thinks that maybe it will not get through? Who thinks it will get through? Who thinks it will not get through? Now I do this. Who thinks that the electromagnetic radiation, the oscillating E field, can easily go through this? Who thinks it will not get through? It's very evenly divided.
So he says it's going up and down. So he's saying the field, the way the radar thing is now, they're set up going up and down. So the antenna is up and down. Right. And, yeah. So intuitively you would say, yes, it gets through the vertical bars, because up and down would mean it has lots of empty spaces. But the truth will be it's still the horizontal one it gets through. And I don't know if he's going to explain why that is. Yeah.
About 25, 25, 25, 25. Okay, we'll see. 1 kilohertz. E field is like this. Receiver is receiving it. What do you...
See, the little dishes look like they're wider than they are tall. So that's sort of implying that the wire's going this way. So I'm just saying that's how it looks.
What do we do first? This or this? Let's do this first.
Horizontal.
Nothing. Not absorbed. Go straight through here. Now rotate it 90 degrees. Now kill it. So in this
so the bars interfere with the polarization in an inverse manner to what you would think is so see, the trick is, right, we're intuitively thinking that the electrons are moving this way, and therefore they're creating polarization this way, when in fact, okay, we know in conductors that the magnetic field is created this way around the conductor. that has a plus and a minus orientation across the conductor. So the electrons might actually, the magnets, the ions, the pressurized atoms might actually be doing this and this rather than this and this in terms of how they affect the world. That is, the bar magnets are in this kind of arrangement: north, south, north, south, north, south, north, south, north, south, staggered. And what they're doing is changing those positions. So what was north, south here becomes north, south down here, and then north, south up here, and then north, south down here. And that change that movement means that it's still in a direction. So yeah, well, continuing.
Configuration, the electromagnetic radiation does not get through. I want you to think about it, and if you have some sleepless nights about it, that's okay too, that's very healthy. I have a second demonstration, and that has also to do with the polarization of...
See, the interesting thing to see is how much of the signal that gets through, what percentage of it gets through, would also be interesting. So even though it's 100% polarized in the correct direction, does 100% of the light actually get through the filter?
Electromagnetic radiation. I have here 75 megahertz transmitter. So that's more like radio stuff. That is a 4-meter wavelength. And this is the antenna. This is the transmitter. Let me give you the numbers. So this is 75 megahertz, and that is 4 meters wavelength. And I'm going to turn it on like now. You don't hear anything. It's not connected to any receiver yet. Oscillating. Making electromagnetic waves, going like this, going up.
Okay, so that's the catch, right? Because the waves aren't going up like this. They're coming off the surface, the round surface, like this. So they're radiating off the round surface as planes. Yeah. So the polarization technically is in this direction. So the antenna is in this direction, the polarization is in this direction.
Not much is going in this direction. I have a very special receiver, a very special one. And that very special receiver is this. It's just a straight copper wire cut in the middle, and the left side and the right side are connected with a light bulb.
See, this is the I really like this experiment. Now this is the one to do with radar, where you're just detecting the energy. So if he did this with a filter, then two slits, then he could see that the signal isn't really light plus light equals dark. That the signal gets through, the frequency doesn't. The energy of the signal gets through. It's just that you can't tune it. So the light bulb will light, but you wouldn't be able to tune it to a frequency. You wouldn't. So you could be sending whatever 75 megahertz, or hertz, whatever he said, and you wouldn't be able to tune it with that antenna through the two slit at certain locations. But if you use this antenna, you'd see the radiation because it would light the light bulb.
So if there's a strong current going through here...
The problem is, to do the two slit experiment at a wavelength that long, 4 meters, you'd have to be 40 meters away from the transmitter. So you have to have a very powerful transmitter to be able to send enough energy that far to light the light bulb, because you're fighting against the R² rule again.
That means if it receives a strong signal, then the light bulb will indicate that. I'm going to make it dark so that we can perhaps see that light bulb. So that is transmitting. And I want to show you several things. The first thing I want to show you is that indeed, if I hold this parallel to the transmitter, that I can receive it. The electric field is now going like this, and so this receiving antenna is very happy.
So again, it's going exactly the opposite way. The signal is going out like this, and the receiving antenna is also lined up the same way to be hit by all of that stuff radiating off the same length. They have to be in alignment. If they're not in alignment, it's like the cardboard example, the slits, you only get a tiny bit of the signal.
But now look what happens. It's the same thing I did with the radar receiver, I rotate it 90 degrees. And now the E field that comes in this cannot cause any current like this. So the light bulb goes out. I can also show you.
But you can hear as he moves the antenna, you can hear his microphone changing. So clearly it's reflecting more radiation. It's doing something.
Which is obvious that if you go farther away from the transmitter,
the less absorption means his radio receiver's getting more impacts because there's less absorption into the antenna.
that the strength of the signal is less. Remember, the Poynting vector goes as 1 over r squared. So the light in the light bulb should go down by 1 over r squared. So I go a little closer, cannot too close because I can really burn out the bulb if I come too close. But you see it's quite bright now. And when I walk away, by holding it still in the right direction, you see that indeed the light bulb gets faint.
So that's the problem with doing this as a 2-slit version, is you have to be about 40 meters and then the bulb isn't going to be very bright unless you have a very powerful transmitter. And then you get in trouble with the FCC and blah, blah, blah.
1 over r squared relationship. What is also interesting, we can explore how much radiation is sent out by this transmitter in the direction of the antenna, which is the direction in which we argued that no radiation should go out. So let me walk over here, or let me walk to the other side, because
it's not that there's no radiation, it's just that there's just a point of radiation, that's it.
Okay, here. So right here, I am now standing such that theta is 0. No matter what I do, whether I hold my antenna like this, or like this, or like this, there's nothing I can do. I can even come a little closer, you see no light. Because there is no energy flowing in this direction. No electromagnetic wave. Largely going out in the plane perpendicular to the antenna.
So again, it's just that it's a tiny pinpoint. But the point is the radiation is coming out of the sides of the conductor. And that's how it has to be thought of. The antenna is a conductor. It's going to behave like a conductor.
But of course, if I'm here, which is not exactly perpendicular, then of course I do pick up also some radiation. Okay, see you Friday.
Oakley doke. So the polarization subjects is really interesting, and you know, I think what has to be understood is, yes, the polarization, that is this kind of being off, being perfect, is really happening this way in the conductor. So the conductor, the polarization is coming off, or the radiation coming off these sides here, and that's the radiation that's each ray is a little bit broken. The more the higher the lower the frequency, there's more capacity for this electron that's producing it to be out of alignment this way. So the electron's wobbling inside the atom this way, not this way. And such. No. So I just said that wrong, because the electron is getting pushed in and it's bouncing back out. So it's going like this. So that's exactly what I'm saying, but I just mean, I should have thought, see, the whole point is the pressure pushes the electrons, it hits them. And if it's, like, say, if it's more black energy than red energy, it's pushing them in. If it's more red energy than black energy, then it's pushing them out. The point is the electron gets pulled in a direction, and then the tension of the other electrons forces it to rebound. It can't break the tension. Well, I'll draw it, because I just want to make sure it's clear that I'm not just talking crap. Alright, got a piece of paper. I mean, I'm going to do videos on all this stuff, but I just mean it's just kind of important to understand tension. So in an atom, we'll just make this a simple one, 4 electrons. And the idea is this tension between these electrons, there's reflections of energy. Back and forth, back and forth, back and forth. And so if these electrons move in this direction, they have to increase this pressure because they'll be getting closer to these other 2 electrons. So for this electron to move in, it has to increase the pressure here, more pressure, because the ping pong paddles, so to speak, will move closer together, more impacts. It'll increase the pressure and force that electron not to do that. So the idea is think of these as rubber bands in a sense, this pressure. The idea is the electron is attracted to the proton. It would like to go there, but it can't because this pressure is keeping it in its location. It gets hit, which means it's going to wobble. It's going to go in, and then it's going to go back out. And as it goes back out, it's going to start getting further away from the proton, which is going to mean it has to stop and go back in again. And then it's going to go out. And it can do that a couple of times, this wobble. So it gets pushed in. It needs to be hit more than once to get pushed in any kind of distance. So it's like a trampoline. The deeper you go in, the faster you come out. And then it wobbles. And so the idea is that that wobble can have a direction. It can come in an angle. So the wobble can be kind of eccentric. In the sense the pressure went in this way, the wobble comes this way, goes this way, goes this way, goes this way, goes this way, until it comes back to its normal again. And so the polarization would be some kind of symptom of the angular difference. So the photon, the first one might leave here, the second one might leave here, third one might leave here. So, and each time it vibrates in and out. So you guys gotta think, when it goes out, when it stops, that's when it releases a little bit. And then it goes back in, stops, okay, releases energy this way. Then it goes back out again, stops, releases energy here. So the point is this is what makes the photon. So this gets converted into the photon, which is a frequency. So the pendulum is swinging. The pendulum swings at a consistent rate. Even though it starts to get smaller and smaller, it's still the same time between swings. And essentially, so the timing is always the same, the distance, the frequency, and that's what makes the different colors of light is just a slightly different speed of wobble. And but the difference in distances they might be at is what's causing the polarization. So polarization would be being a little bit out of alignment as they're traveling. This separation would be the polarization. You can't see that. Close enough. All right. So, till the next time. And such.